Welcome everyone to the GIST Sea Level Rise seminar. We're very glad to have Dr. Meghana Ranganathan, who is an assistant professor in the Department of Geophysical Sciences at the University of Chicago. And her research seeks to understand the drivers and timescales of ice sheet change, as well as how climate and societies will be affected by glacier change. Prior to her current position, Dr. Ranganathan was a postdoctoral fellow at the Georgia Institute of Technology, and she earned her Bachelor's of Arts in Mathematics from Swarthmore College and her PhD in Climate Science from the Massachusetts Institute of Technology. And today she will be talking about the coupling between flow and fracture in ice sheets. So welcome, Megan.
Can you hear me okay?
Yes.
Awesome. Well, thanks everybody for joining and taking the time to listen to some of the work that I've been doing lately, both as a part of my postdoc and since joining the University of Chicago only a few months ago. So today I'm going to be talking a little bit about some kind of initial work that I've been spinning up, trying to really understand what this two-way coupling between flow and fracture is within ice sheets. And based on the audience, I don't think I need to go too much into the background, but I think we're all here because we really care about sea level rise and we really want to both understand the impacts of sea level rise on century timescales, but also really want to understand these uncertainty bars, particularly the contributions of uncertainty to uncertainty from ice sheets. Most notably, the Antarctic Ice Sheet contributes a significant amount of uncertainty to future sea level rise. And we're really interested in understanding the kind of underlying drivers of that change and how we can better constrain that uncertainty. So a lot of this uncertainty comes from these two processes of flow and fracture. Ice sheets are these kind of viscous fluids over long time scales, and that's really what drives a lot of the movement from the summit of an ice sheet out to the continental margins. But then they can also behave like this brittle solid over much shorter time scales. So I think these two pictures are a really nice illustration of that kind of duality of ice, where we have this Piedmont Glacier in Canada, where you can see this really nice kind of flow behavior, where this ice is kind of spilling through a valley through these between these mountains, forming this really nice kind of ring structure. But then on the flip side, this picture from Larsen Sea Ice Shelf in Antarctica shows this pretty significant rift through an ice shelf, which is obviously happening in much shorter time scales. And something that really drives and excites me about glaciology is that we really operate at the intersection of these two kind of otherwise slightly disparate physics fields of fluid and solid mechanics. And we really need to and often do care about both sides of this kind of dual nature of ice, but also really how they intersect. How does kind of the fluid behavior of ice affect the solid behavior and vice versa? And that's really what I'm interested in this talk, and more specifically, really interested in how the kind of smaller scale physics governs that coupling. So obviously, a lot of us think about glaciers on these spatial scales where we're looking at a whole glacier, oftentimes from satellites or being physically there and taking data. If we were to zoom into a sample of ice, obviously we're going to look, the ice is going to look something like this on multiple centimeter scales, where we can kind of take a thin section, put it through a polarizing microscope and see, put it through polarizing light and see all of the individual ice crystals being on the scale of 1 to 10 or 15 millimeters. So each of these small polygons representing a single ice crystal and the color representing the orientation of that ice crystal in space. So I'm very interested in kind of the governing behavior at the crystal scale, and then zooming even further into that on the molecular scale. When we think about ice fracture, fundamentally, in a lot of cases, what's happening is the breakage of bonds. In other cases, what's happening is the kind of opening up of smaller cracks on the grain scale. So this is what ice looks like on that molecular scale, where you can see these water molecules creating these hexagonal features. So I'm very interested in kind of uncovering how the coupling between fracture and flow exists on all three of these scales, and how we can build better physically driven models by understanding these kind of microscale processes. So today I'm going to talk about how flow and fracture are coupled across these scales and what impact this coupling may have on projections of future ice sheet behavior. So the specific problem I was interested in was kind of born out of looking at videos of Pine Island Glacier over the last like 7 or 8 years, and identifying that there's this pretty significant accumulation of fracturing, or what we call damage, in the margins of Pine Island Glacier. And just to orient ourselves in this video, all of this kind of whiter stuff is glacier, darker stuff is ocean. These margins, the ice shelf margins, are designated kind of by these stripes on either side. And as this video plays, this is the video put together by Adrian Luckman. You can see the ice shelf advance, icebergs calve off. But what I'm really interested in is this kind of accumulation of damage in these margins here, and in particular in this right-hand margin. And this video will play again. We can see that this accumulation damage is very significant over the last 7 years and has been, it kind of occurs alongside a pretty significant acceleration, which a lot of people attribute to this damage kind of weakening the margin. What I think is really interesting, though, is the fact that this damage is concentrated in a margin, which is where the ice is experiencing significant deformation, implies to me that there's a two-way coupling, where it's not just fractures opening up and affecting the kind of structural integrity of the ice, but the flow behavior, the deformation, is also affecting the potential for fractures to open up. Fractures seem to open up kind of preferentially in these regions of significant deformation. And so I was very interested in exploring what the nature of this two-way coupling is. And to really drive this home is this really nice paper from Sun and Goodmanson back in 2023, where they did inversions for ice viscosity, or in this case, the ice softness parameter, from 2017 to 2020, so even only just a 3-year gap, and saw this very significant increase in the softness of ice, or the weakening of the structural integrity of the ice, specifically in the margins over this 3-year period. And if we were to kind of look at the optical imagery of this exact same region in 2017 and 2020, we would see that this kind of correlates with this really dramatic increase in damage that occurs between these few years in this specific region, and is likely kind of the best explanation we have for why this ice softness has been dramatically increasing. And so I was very interested in figuring out what's kind of going on in this kind of dynamic feedback between fracture and flow, and how can we better model that. So the typical way that we model this process of accumulation of fractures kind of over longer time scales, weakening the ice, and therefore kind of contributing to more accelerated flow, is through damage mechanics modeling. So the idea behind the damage variable, or damage, is that it's a continuous way of representing fracture in models that otherwise can't really represent discontinuous features. So the idea is, if we define a damage variable D, it can be this continuous variable between 0 and 1, where a damage variable of 0 means the ice is totally intact in some volume, and a damage variable of 1 means the ice has completely lost any of its structural integrity. It's lost all of its load-bearing ability because of the accumulation of crack. And once we have kind of established this variable D, what we can do is kind of put that into our ice flow model. So this is just, what I have here is just Glenn's flow law, or the tensor form of Glenn's flow law, where ice deformation is related to stress through some viscosity term. And we can take that viscosity term and scale it by this damage variable D. So what this means is, as ice becomes more damaged, it becomes less and less viscous, and therefore more and more easy to flow. And this is how many studies have tried to incorporate small-scale fracturing and the accumulation of damage into ice sheet models, and really represents the kind of evolution of this feedback. Once we have this variable D, and a way to couple it to an ice sheet model, all we need is a way to evolve that variable D in time. And the most traditional way of doing it, and as you can see in the citations, tons of studies have used this approach, has used a simple kind of advective transport model, where the change in the damage variable D with time, plus the advection of that D downstream, is equal to some source term. And importantly, it's equal to some source term under a certain condition, which is that the stresses have to be high enough. One can think of this as, if you just have a block of ceramic sitting on a table, it's not just going to spontaneously break. It will only break if you apply some critical amount of stress to it. And the same goes with ice. So the sigma T parameter is the strength of the ice. It's designated T because we typically think of the governing fracture process as being fracture intention. So this is the tensile strength of ice. So in this case, damage only accumulates if stresses have exceeded this threshold of the tensile strength of ice. If they do not exceed that, then there's no additional accumulation of damage. And this is the standard kind of approach to modeling the evolution of damage, but critically relies on these two parameters, the damage evolution function F and the tensile strength of ice, sigma T. And there's been a lot of different approaches to defining primarily this damage evolution function F. There is not, I think, widespread agreement as to what the approach is for modeling this evolution function. And it's really because the evolution function underscores a lot of the really small scale, small time scale, and small spatial scale physics underlying ice fracture. And there's a lot of uncertainty associated with that. So a couple of the approaches. First one is this, what I'm calling the Kachanov approach, which is based in material science work from the 50s and 60s by Kachanov and Rabatinov. And essentially, they assigned this evolution function as a power law. So some B prefactor stress to an exponent. And if you go into their original literature and you look at why it became a power law, it was kind of just a simplicity argument. They state in their paper, thus assuming for simplicity a power law, but no real kind of, I think, physics behind that choice of that power law. That being said, there's been a lot of really nice work lately that have shown that applying this evolution function can actually produce some really nice comparisons to observations. So this work by Alex Huth back in 2023 showed that we can use this model to actually represent a calving event on the Larsen C ice shelf. So there is some physical fidelity to these models. The Albrecht and Leverman approach was from these two papers by Albrecht and Leverman in 2012 and 2014 that proposed that we can scale the damage evolution function by the spreading rate. So the first principal strain rate, and then you multiply some constant by it, and they showed that this can represent some of the fracture features we've seen on Ronnie Filchner. The third really common approach is relating the damage evolution function to the Nye zero stress approach. So stating that that crevasses always open up in tension, and they will kind of continue to advect downwards until you get this zero stress, where the opening up stress, or the first principal stress, is being balanced by the gravitational overburden stress. And so all of these approaches have been used in the literature. The challenge with having a situation where you have many different approaches is it's hard to know, when you're interested in implementing model and ice sheet model, which approach you're actually interested in using. So this is kind of where we started this work. We wanted to understand the coupling between flow and fracture. And really the first kind of question we had to ask is, how do we even model this? There are so many different approaches. What is the appropriate way of modeling damage accumulation? Ultimately, that was kind of the first step in this larger goal of really trying to quantify the effect of damage on future mass loss, and then investigate this kind of two-way nature, the two-way nature of this coupling between viscosity and fracturing. So we start with, how do we model ice damage? There's a ton of different approaches, and where should we go from here? And so we started by setting up a pretty simple flow line model and just wanting to see what happens if we implement one of these approaches. And so we set up a flow line model. So flow line meaning it's only we're only representing the long flow direction. In this case, the glacier terminates at the grounding line, and then it is being forced by some ocean forcing. And we couple it to a transient damage model. In this case, we picked the Kachanov and Rabatinov approach. And we kind of time step forward with month increments to just see the accumulation of damage month by month. And so to orient you with these images, the x-axis is the along flow direction. So right here is where the ocean is. Right here is where the glacier originates. And then the y-axis is depth. So 1 is at the surface and 0 is at the bed. And so what we can see is month by month, this kind of steady accumulation of damage, specifically at the surface. And that's because this is where stresses are high enough for damage to accumulate in the first place. Anywhere too far below, and the overburden pressure is kind of forcing cracks closed, and therefore damage can't open up. So you get this kind of steady accumulation of damage, but importantly, damage seems to reach its maximum pretty quickly within about 4 to 6 months time scale. We were very interested in this behavior, but it really does align with what we would imagine that fracture happens on these really short timescales, likely within a timescale of an ice sheet model time step. And so it's not surprising that as that damage will accumulate very, very rapidly. And so we kind of speculated, well, why do we worry so much about explicitly modeling the rate of accumulation of fracture in these kind of coupled damage flow simulations? Can we represent the same behavior if we approach modeling damage through this diagnostic approach, which is we identify where stresses are high enough for damage to even accumulate, and then we set that to a maximum within one model time step. And we were curious if this produces the same behavior as actually running a coupled transient damage model. And so what we did was we set up the exact same flow line model, but we're testing two different models. We're testing this kind of transient approach where we actually represent the accumulation of damage as a function of this damage accumulation function. And then the second approach being this diagnostic approach where we just identify where stresses are high enough, and then we set that to a maximum damage. And then we run this out for 10,000 years to see if we can produce the same kind of glacier behavior. By glacier behavior, really, we mean grounding line retreat. So in this case, we have three different simulations here. The simulation that's kind of the control is if we have absolutely no damage occurring. In this case, the glacier isn't being forced by anything, so the no damage case just doesn't do anything because we initialize it at a steady state. And then we have our two cases where we're coupling damage to the flow. The first is this fully transient simulation for actually evolving damage at each time step. And the second is this diagnostic approach where we're just setting damage to a maximum at each time step where the stresses are high enough. And we can see we produce basically the same grounding line retreat behavior in both the transient and diagnostic cases. This over these 10,000 years. The right-hand side shows you the percent error in grounding line position. It's percent as a percent of the amount that the grounding line has migrated. And we're kind of well within 1% of a difference between these two simulations. So this kind of suggested to us that the diagnostic model actually can hold and can produce the same behavior, but in a much more simplistic fashion and in a way where we don't have to worry too much about exactly what that damage evolution function is. But this is kind of as just one example, not all that satisfying because it's just one example. So we are really interested in developing an actual theory for why this might be the case. So to kind of understand this behavior from theory, we take the kind of 1D, we take a 1D version of this damage advection equation. Again, in this case, we're using the power law form of the evolution function, but I'll talk in a bit about how this applies for any of those approaches. And then we can non-dimensionalize it. And what non-dimensionalizing allows us to do is pick out timescales to this partial differential equation. So in this case, we can identify two different timescales to this PDE. There's the advective timescale, which is the timescale of glacier flow, which is going to be a longer timescale. And that's the traditional advective timescale is just the spatial scale over the velocity scale. And then we also have this fracture timescale, and that's describing the timescale of the accumulation of damage. Basically, how long does it take for fractures to initiate and propagate? And that we can also define as a function of this power law form. And we can hypothesize that what's happening here is that there's a timescale difference between these two. That in our case, when the advective timescale is far, far larger than the fracture timescale, fractures are reaching their maximum, they're accumulating really quickly relative to our flow timescale. And therefore, that's why this diagnostic model holds, is because we have situations in which what we really care about is the long timescale glacier behavior, but the fracture processes happen on such shorter timescales that maybe we don't need to explicitly model them. So we can define a non-dimensional parameter that is actually a tool that we can use to determine whether this diagnostic model is applicable or not. So this delta parameter is essentially the ratio between the advective and fracture timescales. When this delta parameter is very large, that suggests that fracture is reaching a maximum very quickly compared to the advective timescale, and our diagnostic model should hold. And in this case, then we can, once we have this theory, we can actually probe the parameter space of lots of advective timescales and lots of fracture timescales. So in this case, this side of the parameter space is where ice flow and fracture timescales are very long. And this part of the parameter space is where ice flow and fracture timescales are very short. And what we're seeing on the color bar here is this delta parameter. So remember, when delta is large, we would expect that fractures open up very quickly relative to the flow timescale, and therefore our diagnostic model should hold. And that's generally in this corner of the parameter space here. And then we can run our diagnostic model, and we can run this kind of diagnostic model, transient model comparison for every bit of this parameter space to actually see where this diagnostic model does and doesn't apply. So this is percent error in the diagnostic model as compared to the fully transient model. And we can see what we expected from the left-hand side, that this corner of the parameter space where the flow timescales are very large and the fracture timescales are very small is where our diagnostic damage model performs very, very well, because the flow behavior we care about is very long and the fracture behavior that we are trying to model is very, very short. There are, of course, situations in which this diagnostic damage model would do a pretty poor job at representing things. If we cared about ice physics behavior on very short timescales, so on these kind of timescales, our diagnostic model would perform pretty poorly. So that's just to say that this is not a model that I would advocate to be used to represent calving or rift propagation or any of these very short timescale features. But what we're really interested in, or what I'm interested in this talk, is how does the kind of slow accumulation of damage over years, decades, centuries affect kind of long timescale flow behavior? So for that specific problem, we contend that this diagnostic damage model actually does quite a good job. And we can kind of put boxes around where we think glacier flow and fracture live in this parameter space. Glacier flow tends to happen over longer timescales. Fractures do tend to open up over very short timescales. So in most of the kind of regions of physical values, we think this diagnostic damage model should still perform quite well. Again, if the problem you're caring about is the effect of fracture over long timescales. And so all of these comparisons were done looking at this specific approach, but we've done a little bit of work to show that we can actually boil the diagnostic model down into specific cases of each of these approaches. So by that, I mean, the diagnostic damage model is essentially a case of this power law form in the limit where this prefactor gets very large. And we can actually look at the lab measurements of this prefactor and show that they are in fact large enough that this diagnostic damage model is a good approximation. Same goes for the Albrecht-Leverman approach. This is the diagnostic damage model in the limit where this gamma parameter is sufficiently large enough. And the gamma parameter is something that's tuned by observations. The same is actually true for the Nye-zero stress approach, that this is in some ways a more general form of the Nye-zero stress approximation, because the Nye-zero stress approximation does the exact same thing. It is trying to identify based on the stress distribution where fracture should open, but it has some extra assumptions. For example, that ice has no strength and tension, and fractures are only opening up in tension, whereas the diagnostic model we've produced allows us to represent multi-axial fracture and tune a specific ice strength. We generally think that ice does have some strength and tension, but the exact amount of such strength is pretty uncertain. And we can, in kind of a more 2D setup, we can actually compare this diagnostic model to a whole bunch of these different models. So this is a simulation using the MISMIT Plus setup. So this is now a 2D simulation in IcePack over 100 years forced by basal melting. And we can show that the diagnostic damage model produces roughly the same mass loss as both the Nye-zero stress model and the kind of power law Kachanov-Rabatnov approach. So does something very similar to all of these models, specifically because the problem is within that parameter space where the flow behavior we care about is very long time scale. So all of that to be said, that when we kind of set out to do this, we were very interested in just kind of establishing a model for damage accumulation or understanding the differences between all these different approaches. And what we ended up with is that for this specific problem of how flow and fracture are coupled on long time scales, we may not need to explicitly model the rate of damage accumulation if we're interested in representing the effect of damage on timescales of decades to millennia. And we can develop this diagnostic model that we can then move forward What's really nice about the diagnostic model is that it eliminates a lot of the existing kind of parametric uncertainty in damage models. Basically boils down the uncertainty to one single parameter, which is our stress threshold. And everything else is mostly now removed from the model. And so now that we have a model that we feel good about, we can actually look at what the effect of damage is on long time scales. So how, for example, does Pine Island Glacier respond to a coupled damage flow simulation? So in this case, we zoom in on Pine Island Glacier because it was really the motivation behind a lot of this work, and because it's just doing a lot of interesting stuff. It's accelerating pretty dramatically over the last 20 years. So we take Pine Island Glacier and we set up a simulation in this ice flow model IcePack, and we couple that to our diagnostic model. And we were really interested in how, if we force Pine Island Glacier with observed basal melting, how does this now affect the future evolution of Pine Island Glacier on 300-year time scales or so. So we take basal melt rates from observations from this Paolo et al. Study from 2023, and we can then simulate Pine Island Glacier over 300 years. So our control has no damage coupling. Pine Island Glacier is just responding to basal melt. It loses ice volume over 300 years. But then if we add damage accumulation, we get significantly more mass loss, about a 33% enhancement in mass loss, just due to turning on this damage evolution. Now, there's a lot of uncertainty here, and that uncertainty, as I mentioned, comes solely from the choice in the stress threshold that we make. So at what stresses do fractures start to accumulate? So here, right now, we treat that as an uncertain parameter, and we look at kind of the full uncertainty envelope. So anywhere from our no damage control simulation to a situation where our stress threshold is 0. So ice has no strength and tension, which is traditionally the assumption that underlies the NI0 stress approximation. I also include 2 lines here that kind of represent the lab and observation uncertainty. So there's been studies that have been looking, especially using observations, to try to quantify what this strength value is. They find values that kind of range between about 0.08 and 1 megapascal. So just within that range of uncertainty, we get about a 23% difference in ice mass loss. So all this to suggest that there's a pretty significant effect between underlying this kind of coupled damage flow feedback that may really significantly enhance the ejection of ice from Pine Island Glacier. And all of this, again, is due to the fact that we are accumulating damage. So this is Pine Island Glacier, and the grounding line is as denoted by this black line here. And what we're seeing on the color bar is the accumulation of damage from the start of the simulation to the end. So how much has damage increased? And what we see is significant amounts of increase kind of across the glacier, but especially in the margins of the glacier, which is where we've been seeing in observations Pine Island Glacier damage accumulates, and then some along the ice shelf as well. So the kind of initial probe into this question of what is the effect of damage on ice viscosity suggests that this coupling can result in around a 33% enhancement in mass loss. But importantly, that enhancement is very dependent on what the stress threshold is. And so that's where we enter into this question, really, what underlies that stress threshold? How does ice viscosity and fracturing kind of come together to help us understand what the stress threshold is? So traditionally, the stress threshold is kind of treated as a constant. We look at observations, we look at lab measurements, we try to give us a number for where the stress threshold may lie. And kind of current observations have found 80 kilopascals to 1 megapascal, but ultimately is seeking one number to explain the fracture strength across continent and across the whole continent of Antarctica or Greenland. We've been thinking a little bit about where and what situations this kind of strength value may be not a single number, but in fact an evolving parameter that evolves with material properties and microstructural properties. One example of that is if we were to think about how ice fractures open up kind of on a micro scale, we can kind of do a little theoretical exercise here with this simple kind of schematic of a polycrystal. So this is a polycrystal of 10 grains or 10 crystals each polygon representing a single ice crystal, the lines denoting the boundaries between the ice crystals. If we were to really zoom in a lot to the boundary between ice crystals, they would look something like this, where you've got a lattice on one side, which is one crystal or one grain, a lattice on the other side, and what separates them is the fact that they are misaligned. That's what distinguishes one ice crystal from another, is the fact that they're at an angle from each other. The fact that they're at an angle from each other means that the bonds in between them are quite irregular. So within a lattice, the bonds are very regular. They're these kind of very strong hexagonal shapes. But you can see denoted in this by these kind of green bonds here that the bonds within a grain boundary are pretty weak. They're very irregular. What that means is that the grain boundaries are inherently the kind of inherent flaws in ice that allows fractures to initiate. If we were to stress the sample of ice, we would expect that a fracture would open up along a grain boundary because that's where the weakest bonds are. And then if we were to continue to stress that sample, we would expect that those cracks would continue to propagate along grain boundaries. So this is just a little kind of thought exercise to just suggest that there is some controls on ice strength that come from the underlying microstructure of the ice, the material properties of the ice, how warm is the ice. All of these things kind of suggest that rather than treating strength or ice strength as a single value, it might actually be a more complex phenomenon that is responding to changes in microstructure, temperature, even the viscosity of ice itself might contribute to altering strength. What this means is that we might expect ice strength to actually change spatially and temporally. So ice strength should be different in a shear margin versus in the trunk of an ice stream. And ice strength may be different in 100 years or so as grain sizes grow, as temperatures start to change or internal temperatures start to increase. So this is kind of where we were interested in exploring is what is this kind of two-way coupling between ice flow and ice fracture? That another way of stating that is how do characteristics that typically evolve with flow then feed back to affect the strength of ice and the potential for fractures to open up? So we were interested in producing an ice strength equation that has its dependencies on a whole lot of stuff like grain size or temperature or viscosity. Unfortunately, we are constrained at the moment by just the existence of laboratory data because otherwise there's not really much to base an equation off of. And really the primary good constraints we have on ice strength as a function of anything is grain size. There's been a number of studies, really these kind of three primary studies that have looked at how ice strength, and that's what should be on this y-axis. I keep needing to fix that. Ice strength in megapascals should be on that y-axis. There's been these three studies looking at how ice strength varies with grain size. And they've actually find a pretty clear relationship of this kind of, that can be fit with the best fit line, that ice strength is inversely proportional to grain size. As ice grains grow, you would expect that ice strength to decrease. And that could be due to a lot of physical processes, but it kind of can be understood by that little theoretical exercise I did, which is if we think that fractures are opening up along grain boundaries as grains grow, you get more grain boundary area, and therefore cracks could propagate even further. I don't think that theory has necessarily been proven, but it is an explanation that could underscore the experimental data we're seeing here. But what's great about this is we have a pretty clear relationship and we can pull a best fit line out of this. So we can move forward with, at the very least, understanding how ice strength responds to grain size and how that affects this flow fracture feedback. So what this kind of implies is a replacement of the current look at damage feedbacks than what is traditionally looked at now. So traditionally, this is how we represent kind of the damage flow feedback. We set a stress threshold, it feeds into a damage model, and then damage and stress kind of feedback on each other at each time step as the model runs. This kind of implies a much more complex feedback in which damage and feedback and stress are feeding back on each other, but at each time step, stress is also affecting temperature and grain size. Temperature affects grain size feeds into the stress threshold, which then changes the potential for damage to kind of open up. There's a lot of kind of things to dig in here about how complex this feedback is, but we were really just interested as a first pass to see if we were to implement 3 different simulations, one where you have no damage at all, that's our control, One in which we fix the stress threshold. That's kind of the traditional way people model damage. And then the second simulation where we kind of incorporate all of these different feedbacks, but most importantly, we're representing the effect of grain size change on the stress threshold. How do these simulations of Pine Island Glacier compare with each other? We would hypothesize that we would get more ice mass loss in an evolving stress threshold case, because we would hypothesize that as a glacier starts to flow faster, is responding to climate forcing, grain sizes will increase, and that will reduce our stress threshold and allow more damage to accumulate. That was just the hypothesis we started with. So we went back to Pine Island Glacier, these simulations, to kind of conduct these 3 simulations. So to do so, the first thing we have to do is initialize the model. So we initialize a temperature field. This is just from the heat equation implementation in IcePack. We use that to initialize a grain size field. So this is from, it has its basis in a model that I developed in my PhD from a few years ago. And we can use then the grain size, the kind of initialized grain size, to then initialize the damage field based on this laboratory, this lab constrained equation. Now, notably, what you'll see, this is just our initial damage field, is that there's very little damage. And the reason behind that is that we're constraining these damage simulations with this lab-based best fit line. And it has been noted that lab experiments produce larger stress thresholds or larger ice strength values than most observations would show by quite a bit. Lab experiments generally produce somewhere around 500 kilopascals or so, whereas observations are showing more like 90 kilopascals or 200 kilopascals. So there's a little bit of a discrepancy here, but because the lab experiments are kind of the best we have to explore this grain size effect, we opted to just go with the lab constrained numbers for now, and then explore more later on. So we're seeing very little damage here because our stress threshold has started off so high. But we were mostly interested not in the absolute numbers, but in these comparisons between these different simulations. So in our control case, we have no damage at all. Pine Island Glacier is just responding to basal melting. And in this case, what we see here over 300 years is some amount of mass loss. If we were to then turn on damage and then fix the stress threshold as the initial, so no evolving stress threshold with grain size, we get a little bit of mass loss enhancement, not very much, because again, the stress threshold is set to be pretty high. So we're not getting a lot of damage to begin with. So we get about maybe a 2% enhancement in mass loss by turning on damage, but then keeping the stress threshold fixed. And this is, again, because our initial stress threshold is set to be pretty high. This is about 500 to 600, it's about 600 kilopascals in the margins, and much higher along the rest of the glacier. But we were really interested in what happens if you then evolve the stress threshold in time. The damage change in the fixed threshold case is very little. So what happens if you allow the stress threshold to evolve with grain size is you actually get a significant amount more mass loss, as we hypothesized. And the enhancement of mass loss is quite significantly more than if you just fix the stress threshold. So after 300 years, with just a fixed threshold, we get about 3 to 4% enhancement. With evolving the stress threshold with grain size, we get somewhere close to 13 or 14% enhancement. So we're talking about a factor of 4 increase in mass loss enhancement just by the fact that we're allowing the stress threshold to evolve with time. And the reason that this effect is so significant is, again, because we are allowing that stress threshold to respond to flow conditions. So what's happening physically is that as Pine Island Glacier is flowing faster due to climate forcing, temperature is kind of increasing because of shear heating. That temperature increases, drives an increase in grain size. Reason behind that is due to the kinetics of grain boundary motion. But you get a pretty significant increase in grain size. As grain size increases, our stress threshold drops. And it actually drops quite significantly. It drops about 400 kilopascals or so, which when your stress threshold was initially set to be about 700 kilopascals, that's a pretty dramatic drop. And the reason behind this is, again, those laboratory experiments showed us that there's this inverse relationship between grain size and stress threshold. So your grain size increases, your strength of your ice is going to decrease. And ultimately, this produces more enhancements and damage than if you just fix that threshold and you don't let it move once your simulation starts. Again, all of the numbers, the exact amounts of damage change look pretty small because we are using these experimental numbers that are otherwise set to be relatively high. But you can see that as compared with the static threshold and then grain size evolved stress threshold, you get a significant amount more damage and ultimately produces this factor of 4 or so increase in mass loss enhancement. So ultimately, what I suggest, or what I was excited about this project, is this sort of suggests how important it is to really investigate these microphysical processes underlying ice fracture, but especially underlying what sets the strength of ice, what sets when fractures will nucleate and start to propagate on a microphysics level, and the importance of really investigating ice strength as an evolving feature rather than kind of the set parameter that we're interested in constraining. So I mentioned at the beginning that we were really interested in crafting an equation that would evolve the strength of ice with a whole bunch of stuff, including temperature, but also I think fabric, impurities, all of these things should have an impact. And so we really sought to find experimental data that will allow us to craft this kind of bigger equation. And there actually isn't as much as I kind of expected to find. And I think this is something that I've been very excited about pursuing for future work. The temperature data, especially as we could see, is kind of all over the place. I feel kind of theoretically there should be a very clear dependence on temperature. So far, we're not seeing any of that in experimental data. I think there's a lot of these studies have used very different conditions, different grain sizes. So there's some, I think, potentials for there to be relationships that are being obscured just by the fact that these papers are doing slightly different things. And so I think right now there's kind of a big question mark in a lot of the other factors underlying ice strength. But hopefully, kind of in next steps of the work, we'll actually get to do some experiments and better constrain the effects of temperature, but also fabric impurities and all of these other features that will allow us to develop a really robust kind of ice strength equation that can be put into ice sheet models. So the kind of our takeaway, because this work is pretty preliminary, or this stage of the work is pretty preliminary, the takeaway right now between this kind of coupling of ice viscosity and fracturing is that it exists. There exists a two-way coupling that is more than just fractures affect flow, and that's the only thing that happens. The flow behavior is in fact affecting the potential for fractures to open up as well. And this can be explicitly modeled to affect our estimates for how much glaciers will lose mass in the coming centuries. There's still a lot more work that needs to be done, really establishing the nature of this coupling across a whole lot of dimensions. But we've at least been able to say something about the grain size effect, which is great. And ultimately, the hope is that this will kind of feed into and enhance our understanding of the accumulation of damage that we're seeing in Pine Island Glacier. One example of how some of the stuff we talked about today can help us understand that is a lot of these fractures are seeming to be opening up in shear margins and seem to be opening them up due to something that's happened with the climate forcing. So something has kicked Pine Island Glacier into gear that is allowing it to increase really dramatically in fracturing over the last 20 years. One hypothesis for that could be this grain size effect, that as the glacier starts to flow faster, the margins are heating up and the grain sizes are getting larger, and therefore kind of preconditioning a lot of this smaller scale fracturing behavior to happen. Could be other things. It could be a temperature effect or a fabric effect or some combination. But at the very least, this allows us to start to probe why this dramatic increase in damage in Pine Island Glacier is starting. And then again, ultimately bring us back to the reason that we're here, which is sea level rise. The hope is that we'll be able to use this to understand the effect of this feedback on projections of mass loss and therefore sea level rise out to 2300 or at century scale projections, and be able to understand how this is allowing us to constrain that uncertainty. So just to wrap up, I mentioned that I'm relatively new at the University of Chicago, so building a group right now that's hopefully going to be tackling lots of these similar questions, including kind of the underlying microphysical controls of deformation and fracture, how we take those microphysical controls and put them into models to understand what effect they'll have on Antarctic, but also Greenland ice sheet projections. And then also we're really interested in taking new experimental data, new observations, using them to benchmark these models and understand some of these physics. So I will leave it at that, and I'm happy to take any questions.
Okay, thanks very much, Meghana. And do we have any questions?
Sure, I'll ask a question. So if you have melting, does this always work to grow the grain sizes, or do you ever like freeze in along between the grains and actually end up strengthening the ice? So does the damage function always move in one direction?
No, not always. And it actually is largely dependent on temperature. So grain size responds really strongly to temperature, in that as temperatures increase, your grain sizes tend to increase. But if you had a situation where your ice was getting colder, then you would likely have a strengthening effect. Typically, we were showing here just a case where temperatures were increasing, because that tends to be what we see happening in fast flowing glaciers, that as they flow, as deformation kind of accelerates, then you get the shear heating effect where the ice heats up. But if you had a situation, for example, like you were saying, where the ice would get net colder, then you would get a strengthening effect as well. And I suspect that as we add in more of these dependencies like fabric and impurities, you'll start to get something much more complicated where you could see strengthening as well.
So is that why you don't like the videos you showed were all from a single season? So you don't do you see the damage? Wouldn't expect to see it accumulate from one melt season to the following year, because then it's gone through the seasonal cycle and it's refrozen hard again, or
Yeah, so I think the videos that we were showing, yeah, span many years. I think I haven't really investigated the observations enough to know whether you see similar behavior within a single season. But I know that there's definitely a multi-year trend at the very least.
thanks.
Yeah.
Any other questions? So I was actually wondering about the last point you have on the right here.
Mhm.
So I was wondering how like remote sensing observations or field measurements might help constrain some of the
Yeah, I mean,
properties.
I think there's yeah, a number of different opportunities. I definitely know less about the constraints of the field side of things. What I can say is that having more spatial resolution of um, like velocity and strain rate data can actually help us quite a bit. Because right now, part of the reason that our observations are only really able to give us a single number is because we don't have quite the spatial resolution in velocity to get really fine estimates of of stresses in different regions of glaciers. What that means is we are then kind of stuck in trying to really quantify the stresses at which fractures are opening up in specific locations. So if I go to Pine Island Glacier, it's very challenging to say the fractures that are opening up in the shear margin are opening up at this stress, and the fractures opening up in the center or in the trunk are opening up at a different stress, just because we don't have that spatial resolution of the velocity data. So enhanced spatial resolution of velocity data, better estimates of stresses, I think would go a really long way. I also think that there's a lot that could be done by both by doing in situ measurements where we can actually see cracking. This is something I've been curious about, so maybe others who know more about like ice coring could speak to this. But if we could actually drill an ice core and characterize how cracking differs in different locations, especially micro cracking, like smaller scale cracking, I think that could be really neat to just say, we in an imaginary world, we're able to drill an ice core in a shear margin, and we see much more cracking behavior than we would get in the center or in the trunk of the ice shelf. That would tell us something significant as well. The final thing we could do is taking samples, natural samples into a lab and actually fracturing them in a lab and seeing the conditions under which natural samples fractured and natural samples being taken from different regions. I think all of that together could do a lot to kind of boost our physical understanding of some of these processes. The final thing is I think I'd be very interested in trying to understand the underlying mechanisms of fractures. So even if we have this grain size dependence, what is driving that? And I think that's something that I think laboratory experiments or like actually visualizing fractures opening up in a lab could tell us a lot about.
So would something like NISA provide useful constraints for what you're working on?
I think so, yeah. Yeah, I think both the spatial and temporal resolution of something like that, I think would be fantastic.
Okay. And have you ever looked at some of the materials science work done on cracking in things like aluminum?
I have. Yes, I think the metals literature, so a lot of these theories come fundamentally from the metals literature. I think there's I've been thinking a lot about this. So I think my thoughts are a little jumbled. I think what we can learn a lot from the work on like aluminum or steel is that a lot of the fundamental processes at the grain scale are going to be very similar. And so they've done a lot of work to investigate, for example, these kind of brittle creep or micro cracking processes. The things that are slightly different, metals are usually manufactured to not have any other defects. And glaciers are almost certainly riddled with lots of defects. And so the governing processes in metals might be slightly different than ice. So I think there's something to work out there about how much you can actually take from that literature, given that there's going to be impurities, existing defects, stuff like that in ice. The second is that ice deforms at much higher temperatures than aluminum or steel. And so there's going to be these extra effects or different kinds of mechanisms kicking in because ice is so close to its melting temperature compared to where we traditionally would think of as aluminum steel breaking. Not to say that we can't learn tons from it, but I think there's some correction that we need to, there's some synthesis of literature between the metals community and maybe rock mechanics, because they deal with much more of the existing defects problem as we would. And then kind of combining all of those theories with more lab experiments on ice.
Yeah, and then, so in terms of impurities, like jet engines, the aluminum that's used in jet engines has lots of things added to pin boundaries. And then just on a separate question, so you're not seeing much temperature dependence on the stress threshold in that lab data. Could it be because there are countervailing things going on? So you're growing the grains, but maybe you're releasing stress as you increase temperature as well, and you could have both things happening at the same time.
Yeah, that could absolutely be the case. And if we could do an experiment, so this is part of the reason why I think that there's a lot more room to do a lot of really interesting experimental work. So if you could do an experiment where you essentially pin the grain boundaries and then crack ice at high temperatures, that would really test that potential for grain size to be counteracting a temperature effect. And I think that would be I think that's something that hasn't been done. It would be a really cool experiment. So yeah, I think my hypothesis is that in a vacuum, temperature must have an effect. And what we're seeing here in the experiments is either there just aren't enough of them to see that effect, or there's other things happening when you go to high temperatures that is blurring that effect. And what I would be hoping to do is to help tease apart those different effects by doing things like, can we pin grain boundaries? Can we kind of in some ways force grain boundaries to migrate in low temperature situations, stuff like that.
Sounds like fun. Thanks.
Oh, hello, I have a question, if I may. Thank you for the talk, Meghana. It was very neat results. It's a question more of an ice sheet modeling perspective, I would say. Because at some point you said that all these damage models, what they suggest is that damaged ice flows better in the sense that you have a drop in viscosity, and if you have your SSA model, let's say, that means that your velocity will be higher. My question is, do we have evidence that that is the case? Like, is this correct, what we're doing with models? that ice should be moving faster at those points, or maybe we should just think of cracks and crevasses that at some point will break the, say, calving front in pieces, but the velocity should not be changed?
Yeah, that's an awesome question. It's something I've been thinking about a lot. So the relationship between ice strength and viscosity is something that I think mostly is born out of the material science literature, and we've just borrowed it for the most part. I've done some reading to try to investigate the physical basis for that, and not coming out with much besides it was kind of an easy way of representing. It's born out of something, which is that in theory, one would expect a material that is riddled with cracks to be weaker than a material that is intact. And I think that is seen in a lot of, like we were just talking about, and if you look in the metals literature and stuff, that's definitely the case that something that's cracked is going to deform or further crack at lower stresses. So that effect is known. Whether what the actual way of modeling that effect is, or what the physical basis is for ice, is deeply unclear to me. And I think you could be right that especially when it comes to, we're trying to model fractures across a whole lot of scales. I think a rift is going to have a really different effect on ice dynamics and the flow field than all of this microcracking work that's really being done in the material science literature. So I think it's totally plausible that crevasses and rifts don't have this effect in the same way that we are modeling it as. And it's something that I've been thinking a lot about how to what the actual physical model ought to be for that coupling. But I think there's a lot of different theories I'd be happy to chat about in the future. But I think you're possibly right that this is not the best way of doing this.
Thank you.
Yeah.
Okay, do you have any other questions? I saw Allegra said in the chat, can you temper an ice sheet? I guess.
Yeah, Allegra, can you explain what you mean by
uh,
temper?
I was just kind of joking, but just thinking about like the analogies with metal, like that's what you do. You heat it up and then you cool it down in a controlled way, and it actually ends up, that's why it doesn't shatter. You can make blades out of it, right? But
Yeah,
I'm
I
also
think
just kind of joking because this is a cool topic.
I think probably the short answer is yeah, if you take a sample of ice into a lab and you try to do something similar to tempering, you can control the grain size, you control um, the ways that air bubbles get squeezed out and stuff to make it even stronger. Yeah, at the ice sheet scale it would be a challenge, but I think in theory you could probably do something similar in a lab. There are experimentalists on the call who could probably answer that better than I could.
Okay, well, we're about at the hour, so I guess we can stop there. So thanks again, Meghana.
Yeah, thanks everyone.